Hello and welcome back. We're going to talk about pressure and depth in a static fluid. This strange little diagram that we're looking at here, we're looking at an image of a cube of water in the middle of the water. Okay, so it's a strange thing, but this is a concept that you'll see in almost every physics book. So let's flesh this out a little bit. This cube of water is experiencing pressure from above and below and both sides. Now we talked about pressure as a function of depth in a fluid, so it would stand to reason that the pressure on the sides of this cube of water are all the same, pushing in from the sides, but the pressure pushing down on the top of whatever area this cube is, and the pressure pushing up from the bottom are different because the bottom pressure is deeper and bigger. So since pressure equals force over area, force equals pressure times area. So here we have our classic, it's the second most important thing ever from Physics 1 mostly. The net force in the y-axis equals the force up minus the force down. Now there's one upward acting force, that's the pressure pushing up from the bottom, so pressure times area. And there's two downward acting forces, the pressure from the top and then the actual weight of this cube of water. So, since the net force on our cube of water under the water is 0, then we can say that the pressure at the bottom equals pressure at the top, force of the pressure at the top, ooh, that makes me mad, plus the weight. And the mass is actually, since density equals mass over volume, mass equals volume times density. So we'll take that into account. And hey, since volume equals area times height of our cube, then we can say P2A equals P1A plus rho VG or rho AHG. Why we pulled area out of there is for the simple fact that we can cancel it out. It appears at every term. So P2 equals P1 plus rho GH. That's an important equation. We will use that several times. So the deep pressure, the pressure further down in our column of water, equals the top pressure plus density times height times G. So we can use that even if we're talking about atmospheric pressure as the P1. So here's an example, Lake Mead, talking about the Hoover Dam, not the Hoover Seam. Hoover Dam, the only factor here is actually the depth, not the breadth, not the length, not the volume of water. It's only the depth of the water for the pressure and therefore the force that would be exerted. Another example here is to talk about diving underwater. So you're at your local lake and you dive down 5.5 meters. You're really going to feel that on your eardrums. Points A and B are located a distance of 5.5 meters beneath the surface of the water. Find the pressure at each of these two locations. It's the same. It doesn't matter what's above it. It matters how deep it is in the water. Now we're going to call P1, our first pressure, the atmospheric pressure. That's the pressure of the atmosphere sitting up here pushing down on the surface of the water, plus rho, the density of the water, times G times the depth. So we get 1.55 times 10 to the 5th Pascal. So we're used to a certain amount of pressure from atmospheric pressure, and then when you dive underwater, water's a lot more dense than air, and so you'll feel a lot more pressure on yourself. We use this concept with things like a mercury barometer. If you ever look in one of the chemistry prep rooms, you'll see that we have a couple of mercury barometers, and what happens is that atmospheric pressure pushes down on this liquid layer of mercury, and mercury raises up this evacuated tube, and depending how much the pressure pushes, we'll be able to measure this column of mercury. So this is a way that we used to do it. So 760 millimeters of mercury is standard atmospheric pressure, and some units use that. Now, sometimes you don't actually care what the pressure is. You want to know how much the pressure is above atmospheric pressure. So my tires and my car, I'm not reading what the actual pressure is. I'm reading the gauge pressure, the pressure above atmospheric pressure. So the absolute pressure is P2, but when I subtract that from atmospheric pressure, I get rho GH, and here's the gauge pressure inside my tires, so maybe it's 36 psi. That's not the actual pressure, but that's the gauge pressure. Blood pressure, we measure blood pressure. There's all sorts of instances where we'll measure pressure. Now, another quick thing to toss in here is Pascal's principle. This lends itself, this is a way that physics helps us do things. Turns out that inside a completely enclosed fluid, like that hydraulic jack you have in your trunk to jack up your car if you get a flat tire, that hydraulic jack is using this principle. It's not built quite like this, but cut us some slack here. There's a narrow piston and a thicker piston. The narrow piston has a small area, and the thicker piston has a larger area. And what we're able to do is manipulate what we know, pressure equals force over area, to come up with this idea here that F1 over A1 equals F2 over A2. That means that the force that I put into piston 1, the narrow one with the smaller area, is going to generate the same pressure that is going to be reflected through the whole thing. And so over here, that same pressure with a larger area is going to come up with a larger force. So F2 is going to be enough force to lift the car. F1 is my input force, and then that ratio of the area of the two cylinders is how much I'm magnifying my force by. So when I jack up my car, I'm able to come up with a huge amount of force and lift up my car, even with a relatively small force coming from my hand pumping the jack. So here's the example. The input piston has a radius of 0.0120 meters. The output plunger has a radius of 0.150 meters. So if the combined weight of the car and the plunger is 20,500 newtons, suppose that the input piston has negligible weight and the bottom surface of the piston and the plunger are at the same level, what is the required input force? So again, pi r squared, so we have to make sure we do the area part correctly. But you can see here that I'm magnifying my input force by a lot to get to this output force. 20,500 divided by 131. I'm magnifying my force by 156 times in order to do this, which is pretty cool that we have access to that. Turns out in the world of physics you can't get something for nothing, so even though I'm magnifying my force by a lot, I'm going to have to apply that force quite a bit. So if you're ever jacking up your car with a hydraulic jack, you have to pump it a bunch of times in order to get it to move up. Okay, this is a big concept, Archimedes principle, and we will tackle that in just